Hello guys, this is John Perham here. I'm going to run through the solution to last week's test problems. There were two sets of problems, the green ones and the yellow ones, and we're going to do both of them. So let's start off with the green problems and question one. So question one, what's it about? Well, we want to find the parametric vector form for a line connecting points with coordinates there, 1, minus 2, 4, and 3, minus 6 and 4. And when we've done that, the second part is to find the Cartesian form of this. So to find the parametric vector form, we subtract the second vector, or the first vector from the second, and then the parametric vector form is equal to the first vector plus some parameter lambda times the difference. And we can do that, and we can visualize it like so. So that's the first part of the question. And now we want to find the Cartesian form, so we set up the components of a vector of Cartesian coordinates x, y, z using that, and we get some equations for lambda. If we take this vector away from this one, then each component has to be 0, and they will, so let's do that. There's some equations, and if we look at the equations, we can see that the last one, the equation is 4 minus z equals 0. So we can find that solution easily enough. And then if we add twice the first equation to the second one, then that will get rid of the lambdas, and we'll get that. And then we can solve that for y. So that's the Cartesian form. So that was easy enough. So let's go on to question 2. And so we set up this vector of b's using this b1, b2, and we can view that as a column matrix using that, and we're asked to find the condition that this vector is in the span of the three vectors here, and we can view those as column matrices using that. So they're the three vectors. So the question is to find the values of b such that it's in the span of these vectors. Well, what does that mean? Well, that will be the case if we can find three parameters, or values of, say, three parameters, lambda, mu, and nu, such that the vectors got by taking a linear combination of the three vectors and subtracting off the vector of b's, is if we can find those lambdas. And anyway, so this is a set of 4 linear equations for the three parameters, lambda, mu, and nu, and we can find the coefficient matrix by looking at the coefficient of the one of the parameters in each equation, or each of the parameters, and that's done by doing this, and we can look at that as a matrix, and it looks like that. So that's the coefficient matrix, and now we want to calculate the right-hand side vector, so we multiply the coefficient matrix by, or we multiply the parameters vectors by the coefficient matrix and subtract off the equations, and that will give us those, and of course we knew that. And then we can define an augmented matrix by putting those together and viewing it in matrix form like that. So this is the augmented matrix, and we now want to perform row reduction on that. So we want to do that. We want to get perform operations so that these become 0. So that means we subtract 3 times the first row from the second and 5 times the first row from the third and the fourth row. So we can do that here, and then we can check that that looks okay, and there it is, and you have indeed got zeros down. And now the second phase is we want to subtract this row from this row. That will give us a 0 here, and twice this row from this row, and we can do that. And we can view that in and we can see that these will only have a solution if this row and this row are non-leading, and this one, and that will be the case if this quantity here and this quantity here are both 0. So that's the condition on the B's that for that system, or for the vector B to be in the span of those 3 vectors, that both of these have to be 0. So that's easy enough. And now we go on to the third question, and we're asked to find the inverse of the matrix whose rows can be entered using this, and we can view that as a matrix. Well, the way we do that is we can establish an augmented matrix by joining the rows of this matrix, or each row of this matrix, to the corresponding row in the identity matrix, and we can do that using that, and then we can view that in matrix form using that. So we can see that over here we've got the unit matrix, and here we've got the original matrix. So what we want to do now is we want to perform row operations on this matrix so that this matrix here becomes the unit matrix, and then what's over here will be the inverse. So in other words, row reduction, so we will add twice the first row to the second row, and that will give us a 0 there, and we subtract the first row from the second row, and that will give us a 0 here. And we can do that arithmetic using this and look at the matrix to check that it's okay, and there it is. We've got it like so. And the next thing we want to do is to swap this row with this row. And if we do that, and view it, we can see that that this matrix here is in row echelon form. And now to put it into to finish the job, we have to perform row operations so that those 2 elements and this one become zeros. Okay, so if we look at that, we can see that we can do that by adding 5 times the third row to the second and subtracting twice the third row from the first. Okay, so that is done with this, And so that's the new augmented matrix, and we can see that that indeed has produced zeros here. And now the last phase is to subtract 4 times this row from this row. Oops, from the first row. It doesn't want to cooperate, and we can do that using this. Oh, we also want to multiply this row by -1, so we can do both of those at once. And if we view this matrix here, we can see that we've indeed got the unit matrix here. So what's over here must be the inverse of the matrix A. So we can establish that by pulling out those elements. So we take each row of the matrix, and then we go from we take at columns, the elements in columns 4, 5, and 6, doing that, and that gives us the unit matrix, sorry, the inverse matrix. And we'd like to check that that's correct. So if that's correct, then if we multiply this matrix here by the original matrix A, then that should be the unit matrix, and we can do that, and indeed it is. So that's the inverse matrix there. Right, so that was the green problems. Now let's do the yellow problems. So we take the first one. So we're given that A, B, and C are invertible n by n matrices, and we're asked to simplify this expression here. Well, let's write it down. So that's it here. Now if we look at this bit here, the inverse of b to the -1 c times a to the -1 is equal to a to the -1, c to the -1, and b. And we can see that we've got a b times b to the -1 here, so that's just the unit matrix, and we've got a times a times a to the -1, so that's just a. And so we can make those simplifications, so the answer is a times the inverse of c times c transpose, and we can't do any better than that. So that's the answer to that problem. Let's move on to question 2. We're given, we can enter the rows of the two matrices A using that, and B using that. And if we can view those as matrices using that and that. So and we can see that the number of rows of the first matrix is equal to the number of columns of the second matrix. So that's the condition for the product to exist. So how do we calculate the product? Well, we take a sum over columns of basically the scalar product of each row with the corresponding column in here. So this would be the 1, 1 element of the product. And we do that for each column of A and row of B, and we'll call that the product matrix P, and we can see that that is a 2 by 2 matrix, which it should be, which we can view as a matrix like that. Well, you shouldn't be surprised to know that Mathematica can carry out the product of matrices. So it's a black box, if you like. So we can check our result by using that, and we can see that the result is exactly the same as we've got here. So that's the answer to that problem. And now we go to check question 3. We're asked, does the point with coordinates 3, 0, minus 1 pass through the point with coordinates, this one, spanned by 2 vectors whose elements are this. So that's the vector. We'll better execute all this. So that's the first vector, that's the second vector, and that's a point on the plane, or the span of the two, and we define the coordinates of the other vectors as A equals this one here, and B equals this one here. So, in other words, does the vector or the point lie in the plane? Well, if it's spanned by the vectors A and B, then its parametric equation will be the first point plus a parameter lambda and another times A and another parameter mu times B. So let's calculate that. And so in other words, this should be equal to the original point. So let's call those, establish those parameters, lambda and mu, and we have to find values of those such that the difference between this parametric vector equation of the plane is equal to the coordinates of the point. So that will give us a set of equations which need to be all 0. In other words, can we find values of lambda and mu such that these 3 linear expressions are 0? Well, that's again a problem in linear algebra, so we regard these as a set of linear equations equal to 0, and we can find the coefficient matrix by looking at the ith equation and the jth parameter, and we do that over the number of equations and the number of parameters. And that coefficient matrix looks like that, and we can view it as a matrix like that. Well, we have to calculate the right-hand side vector. So to do that, we multiply the matrix by the vector of parameters and subtract off the equations. And we can visualize that using that as a matrix, and then so we can now construct the augmented matrix by taking each row of the coefficient matrix and appending the corresponding element of the right-hand side vector for each row of the matrix. So that's it here. So we do it over the number of rows in the matrix C. And there we go. And we can look at that matrix like so. And so now to proceed further, we do the row reduction. So we want to get zeros here and here. So we do that by adding 3 times the first row to the second row and adding twice the first row to the third row. So that will be done using that. And we can view that in matrix form, like so, using that. And we can see that indeed we've got zeros here. And now what we want to do is to try and get a 0 here, and hopefully we'll get a 0 here. So we do that by subtracting twice the second row from the third row, from 11 times the third row. There we go. 11 times the third row minus twice the second row, and that will give us this. And we can view that as a matrix. And if we now go back to the original equations, those equations, the corresponding to the bottom row, will be 0 times the first parameter, lambda, plus 0 times mu, which is 0, is equal to minus 54, and that can't be true. So in other words, the equations have no solution, and therefore the point does not lie on the line. Goody. So we're almost there. Let's go to the last problem. So we now want to set up a set of linear equations for some variables which we can generate using that. So they're x1 up to x4, and we want to write down the equations, a set of linear equations that they satisfy using that, and we can view those as a column matrix. So all of these have to be 0. So we've got 3 equations in 4 unknowns, so we can't we won't have a unique solution. But let's dig out the coefficient matrix using the usual and then we can generate the right-hand side vector by multiplying this coefficient matrix times the variables and subtract off the equations, and that gives me that. And then so that's the right-hand side vector. And now to get the augmented matrix, we join, if you like, this vector onto this matrix here, and we can do that using this. And there we go. So we start the row reduction. So we want to subtract twice this row from this row, and then we want to subtract the first row from this row. So we can do that arithmetic using this and view it as a, and we can see that that's given us zeros here and here, and now we want to get zeros here and here, sorry, a 0 here, so that tells us that we should subtract twice the second row from the third row. So we do that using this third row of this matrix minus twice the second row, and there, that gives us that, and then we can view that as a matrix using that. Well, what do we got here? Well, we've got we can see that the last row is non-leading, so the corresponding linear equation will be identically satisfied. So we don't have to worry about that. So the equation corresponding to the second row can be got by doing this, corresponding the second row, take the times the variables. So this is an equation. This has to be 0, and we can see that this is an equation which we could solve for x3 as in terms of x4. So we set that equal to 0, and we solve for the third variable, x3, and there it is there. And we now want to substitute that into the equation corresponding to the first row. So we take the first row of the row reduced matrix and take the scalar product with the vector of variables, and then we want to replace x3 in whatever that is by this here. So we do that, and we can see that this is an equation which involves x1, x2, and x4. So we can set that equal to 0 and solve, for example, for x1. So that's the first variable. So we can carry out that simple solution using that, and thus we can find the general solution to those equations using this. So we take the variables and we replace the x3 and x1 by the solutions we've found, and we can view that as a column matrix where we replace x2. We can see that this depends on x2 and x4. So we can replace x2 by some parameter lambda and x4 by some parameter mu, and that will give us that. So that's the general solution of those equations, and we can see that that's a 2-parameter family of equations. And all we need to do is now check that that is indeed a solution, the solution. So let's go up here a bit. To check, we put these expressions for the solutions into the original equations, and the result for that should be a vector of zeros, and there it is. So that is the solution to that problem. So that's all of those. So look forward to seeing you all tomorrow.